So today we're going to discuss the history of the atom, looking at different models and how we came to the current model of the atom. So, a lot of scientists, Dalton and others, had a lot of questions about the atom. We want to know, what causes them to stick together to create these compounds. Is the atom composed of parts? Because as of right now with Dalton, the atom is the smallest, component. We don't know anything about its internal workings. And then the third question was, is it possible to break up the atom into its components, if it does have these parts? So Dalton's atom, basically, from his 5 postulates, since he said the atom was the smallest unit, it's basically this ball, or this kind of cue ball or billiard ball. We don't know what's in it. We don't know how it works. So pretty simple. After him came along a guy named Thompson, J.J. Thompson, in the late 1890s, and he did a lot of experiments with atoms, and he found that atoms of any element could be made to emit these tiny negative particles. So that must mean that the atom has these negative things. And so we said, okay, well, all types of atoms must have these negative particles then if they're emitting them, and we're going to call them electrons. But since we know that the atom is neutral, it's not positive or negatively charged, we've got to have something that can balance out that negative, or balance out those electrons. And so he said, well, it's got to also contain some positive stuff. We don't know what that's called, we don't know what it looks like, but we know it's got to have both. And so using his information, a guy named Lord Kelvin, his real name was William Thompson, he's not related to the other Thompson guy, and that just makes things a lot more confusing. So we're just going to call him Lord Kelvin. He came up with what's called the Plum pudding model. Well, in the 1800s, plum pudding was really popular, probably not so much now. So I would think of it kind of like a chocolate chip cookie. The atom itself is like the cookie part, or like the pudding. We've got this positive stuff, okay, and so we've got a pudding, or the cookie is positive. And then we've got enough electrons, because we know we have these particles called electrons, scattered in that are going to balance out the positive charge. So they're calling these plums, but if we're using the cookie example, I would say the electrons are kind of like the chocolate chips, and the positive part is the actual cookie itself. Okay, so we've got these electrons, and we have this negative stuff. And so then a guy named Ernest Rutherford came along in 1911, and he did an experiment with the atom, and he shot alpha particles at a piece of gold foil. So he used gold foil because it's only going to contain gold atoms. If you want to go a cheaper route, you probably could have used aluminum foil. Not sure it existed then. And so alpha particles are positive. So we shot these positive particles at these gold atoms. Now let's think about the plum pudding model for a second. So we've got this atom, and it's mainly positively charged, and we have some negatives kind of thrown in. If we shoot positive particles at it, well, we know that positive and positive repel. So if this atom is mostly positive, these positive particles are most of the time going to hit something that's positive. And so we would expect all of those alpha particles to reflect back towards the emitter. The very few alpha particles that hit these electrons are going to be allowed to go through because they're going to attract to the negative. So we would assume that we'd have a few alpha particles over on the other side, but most of them are going to reflect back toward the emitter. We'll take a look at the picture. The exact opposite happened. Here's our emitter. Okay, very few reflected back, actually, and a whole bunch went through. So that tells us that this plum pudding model is probably not correct. Okay, so most of the particles pass straight through the foil. That tells us that there isn't this, large amount of positive stuff, because otherwise they would all reflect. Some were reflected back at large angles, and some reflected exactly back. And so that says, well, there's got to be this positive thing, but it's not throughout the whole atom. And so that meant that the plum pudding model probably didn't work anymore. And so Rutherford modified the model to say, well, okay, there's still got to be this positive stuff, but it's very concentrated and it's small. And then maybe the rest is empty space or something, they didn't really know. So instead of the entire atom being positive, they said there's got to be this tiny part of positiveness in the atom, but it's not overall. And so then that developed into what's called the nuclear atom. So the nuclear atom is an atom with a dense center of positive charge, And then we've got all these electrons kind of moving around the positive charge in a space that's otherwise kind of empty. So that explains why most of the alpha particles were able to go straight through, because there's all this empty space or these negative things. So the nucleus, so we've got another new term, is the dense center of positive charge, and it contains what we're going to call protons. Proton has the same magnitude of charge as the electron. So like if an electron is -1, proton is +1, but its charge is the opposite. It's positive instead of negative. So that's our positive component. And then within the nucleus, we also said that there's what's called a neutron. So it's another part of the nucleus. It's a little more massive than the proton, but it's neutral. Okay, it has no charge, and that's where neutron is coming from. So let's take a look at this nuclear atom. Okay, so here's the atom as a whole. Okay, we've got that center part is our nucleus. And so here we've got the red ones are the protons, those are positively charged. Our white ones are neutrons, those are neutral or zero. And then around, so you can see it's small and dense. Now, a lot of models show it being in the center. It doesn't have to be in the center. That's just kind of how we usually draw it. And then we've got our electrons kind of orbiting the nucleus. So sometimes this is also called the orbital model because or the planetary model, because the electrons are orbiting the nucleus kind of like planets. Well, this led to the modern atom, which is really similar, except we kind of defined the size more. So we said that the nucleus is really, really concentrated and tiny. It's 10 to the negative 13 centimeters in diameter, which is really small. You obviously can't see that with your eye. And that the electrons move around the nucleus at quite a large distance, so a distance of about 10 to the negative 8 centimeters. So if that's kind of hard to picture, if the nucleus were the size of a grape, the electrons would be about a mile away. So think about a grape and then go a mile from there, and that's where the electrons are. So there's quite a lot of empty space within that tiny atom. Okay, so from there, and we will talk about these other ones in more detail later, but the Bohr model came next. So he said, okay, well, he's going to go along with the same type of stuff as the nuclear atom, except now we're going to say that the electrons are occupying these specific orbits, and so they're going to travel in these very specific paths around the nucleus. So from there, we went to the electron cloud model, which I would say is probably our most current version. And so instead of these specific paths, we have what are called electron clouds. And so the clouds can be different shapes, and we'll talk about that later. But basically, we say, okay, electrons are somewhere in this cloud around the nucleus. We don't really know where they are or how they get there, but they occupy this shape. Okay, so let's talk a little bit more about those components of the atom. So we've got three particles in the atom, the electron, the proton, and the neutron. Well, we know that the electron has a relative mass. Now, relative mass means we're comparing it to other objects. It's not necessarily its actual mass. So if we give the electron a relative mass of 1, we know it's got a charge of -1. Well, the proton has a charge of +1, but look at the relative mass. It's so much bigger. So electrons are really not very massive at all. The mass of the atom is coming from the proton and from the neutron. So these are making up the nucleus, much more massive than the electron. And we know the neutron has a neutral charge, or charge of 0.